Swayam Prabha. Digital India. Educated India.
Dear viewers, in this lecture, I would like to discuss the impact of growth in urbanization on surface runoff and how the tools of remote sensing and GIS can be utilized for making an assessment of the same. First of all, let us look at what actually is urbanization. In the early days, people used to cluster in very small relative areas, and the growth activities or the normal day life activities would be carried out. These would be the hub centers of activities in terms of administration, cultural, religion and other related activities. It has been found that in India, the rate of urbanization has enhanced many folds along with the rise in population. It is estimated that in the year 1975, about 21.3% of the total population used to live in the cities. However, due to migration from the rural areas to the urban areas, it has been found that in about 29 years, this has grown to about 28.3%, which means that about 7% more people have moved into the cities, and there has been also a combined growth in the population during this 30 years, which means that there is a tremendous pressure on the use of land in and around the city areas in order to accommodate various facilities which migrating people may require in terms of housing, various infrastructure like roads, water supply and other activities. So, let us look at, with the growth in urbanization, what are the issues which are involved with this. First of all, there is a decrease in the pervious area and increase in the impervious area, which means that the natural ground is converted for human activity and thereby the ground characteristics change. Well, this leads to a dynamic change in the land use and land cover. That is, natural grasslands or vegetation or agricultural areas are converted for man-made use and thereby dynamically changing the land use and land cover on a regular basis. With the growth in urbanization, now let us look at what are some of the issues which are involved with it. First is, there is a decrease in the pervious area and increase in the impervious area, which means that the natural ground is converted to hard cover top areas such that there is a continuous and a dynamic change in the land use, land cover. The natural land which may be earlier be in the form of grasslands or being used for agriculture or maybe natural forest is now being converted for human activities, thereby changing the characteristic of the land. With this dynamic change in the land use, there is naturally a change in the hydrological cycle. The impervious areas bring about a very unique phenomena of enhancing the movement of water over the land surface, because it is no more possible for the water to percolate into the soil and go into the groundwater. Thereby, it creates a dynamic and conflicting water demand, because earlier the water could percolate and go into the soil profile and reach to the groundwater reservoirs. Now, this water moves over the surface in a much rapid manner and reaches to the rivers from where the water is conveyed downstream, thereby creating a larger dependency on groundwater. With the depleting issues of groundwater already due to impervious areas, it creates more demands on the supply. Naturally, urbanization would bring about other forms of activities, and one of them could be the enhanced industrial activities, which would mean that there would be more demand of water, and thus a spiraling cycle of more dependency on the groundwater would come to existence, which means that there would be more human interventions over a period of time, and these interventions could be in the form of various other interests which human beings would like to incorporate into the urban areas. Well, all these activities have one profound impact, and that is that there could be enhanced or increased pollution in the region. The pollution could be in the water bodies, the pollution could be into the soil profiles, the pollution could be in the air, and thereby with the enhancement in urbanization, it creates and brings about many problems which are there. The main problem which could come into existence is the deficit in the water balance in that particular region. So, with these issues under consideration, now let us look at what is the impact of the hydrological effects due to urbanization. On the left hand side, a schematic diagram of an area prior to pre-development has been shown. One can see that this particular area is having abundant open spaces along with green vegetation, and the soil is pervious in its nature. Thus, there is going to be interception of rainfall due to the vegetation. Some part could be lost due to evapotranspiration, but by and large the water would be available onto the soil surface, which is pervious in nature. Depending upon the soil moisture condition, the water can percolate into the soil profile, and thus there would be less amount of runoff on the surface and more infiltration, which would mean that there would be more water availability onto the groundwater storages. These groundwater storages are important both for human life and for flora life, because availability of water means subsistence of human beings and also of green vegetation. Now, let us look at the impact that could come due to urbanization. On the right hand side, the same piece of land has now been converted into urban area. One of the major factors is that the pervious soil areas have now been replaced by impervious surfaces. There is less amount of vegetal cover also. So, when the rainfall takes place, the amount of rain reaching to the ground is much more faster, because the green vegetal cover is not intercepting the rain, and thereby there is no cushion factor or delay or a mask layer which is holding the water. So, all the water is now reaching onto the impervious surfaces. These impervious surfaces will not allow the water to percolate onto the soil profile at a greater rate as in comparison to the previous scenario. The net effect would be that there would be increased availability of water to flow over these surfaces, and thus what will happen is less amount of water will percolate. So, the recharge to the groundwater reservoirs will also decrease. So, if we look at the hydrological effects of the urbanizations, it would be less infiltration, more peak runoff, generation of wastewater, disposal of wastewater, disruption of natural water balance. There would be increased flood peaks, floodplain widening will take place because more water is available. Since the quantity of water which will be reaching the streams would be larger and their time of concentration will also be small, so there would be flashy floods. Similarly, with the increase in the rainfall events, the flooding frequencies will also get increased. However, during non-rainfall periods, since the water has not been able to percolate through the soil profile, what will happen is that during the dry flows, there would be less amount of base flow during dry seasons. That is, the rivers will reduce in their width, carrying lesser water, because there would be no contribution coming to the base flow from the groundwater reservoirs. So, it means that with increase in urbanization, there is going to be a disruption into the water balance in that particular region. As and when rainfall will take place, there is a likelihood of flood also coming along with it. The other aspect would be that there would be lesser amount of water which would be reaching to the ground water reservoir storages, and thus during low or dry season there would be low base flow and there would be lesser amount of water available in the river streams, and thus a total change in the hydrological cycle will take place. So, now let us look at the flow chart of urban hydrology. The starting point is naturally the precipitation which is occurring. Based upon the interception, that is the vegetal cover, the rainfall would be intercepted, and this will act like a sponge, storing water for some time and then releasing it slowly so that it can be absorbed efficiently by the soil profile, and through infiltration process it can reach to the groundwater reservoirs. With enhanced impervious surfaces, what will happen is there is going to be a rainfall excess which will contribute to the overland flow. From the overland flow, some portion may get evaporated. As the rainfall is falling, some is infiltrating into the soil profile. So, the process of transpiration will also entail a certain amount of loss, where the water vapors would be released into the atmosphere, into the air, and this is what we call it as evapotranspiration. This is a loss factor in the hydrological cycle. When there is lesser amount of pervious surfaces in a region, what will happen is that due to excess rainfall, the overland flow volume will get enhanced, and thus there would be more availability of water onto the streams, lakes and reservoirs, and depending upon the volume that it can sustain, the risk of flood would be associated. So, it is a very complex cycle wherein urbanization is important to meet the needs of the human beings, but on the other hand, it enhances the risk of flooding, loss of water at a faster rate, and lesser infiltration into the groundwater reservoirs. Coupled with this, to meet the demands of the human beings, there would be another component which has to be taken into consideration, and that is the wastewater. And to treat this wastewater, there is going to be a further consumption of water which would be there, and thus the net effect is that the demand will rise, but the supply will reduce drastically. Another factor which we must take into consideration due to urban hydrology, and that is the process of sedimentation into the nearby water bodies. As we have already discussed in our earlier lecture, that due to sedimentation and other depositions of other material, the water carrying capacity of the water bodies may get reduced. Further, depending upon the type of material and its chemical composition, there can be a change in the water quality. This water quality may convert the water from potable to unpotable, and if some water bodies are sources for human drinking purposes, they need to be then supplied after they have been treated at a treatment plant. This again means that there would be additional demand of water. So, we can now understand the complex cycle that urban increase can have on the runoff pattern or in the hydrology of a particular area. Keeping in view the impacts of urbanization, I am now going to focus on a study area which is in the state of Rajasthan in India, close to a place called Ajmer. Ajmer is situated about 132 kilometers from the capital city of Jaipur of Rajasthan, located between the latitudes of 26 degrees 20 minutes north to 26 degrees 40 minutes north and longitude 34 degrees 35 minutes east to 34 degrees 55 degrees east. On the right hand side, you can see the index map of the district map of Rajasthan, and below we can see the district map of Ajmer, and on the left hand side you can see the satellite data of the Ajmer fringe, as it is called. Ajmer is known for its importance in terms of religion. There, a very important religious place is there, and every year there is a major festival which takes place, bringing millions of people and devotees to that particular place. So, there is a sudden demand of water in this particular region, and also enhancement in the deliverance of wastewater. First of all, we have to meet the supply of the water, and the supply of water is met through two reservoirs which are closely located to the city of Ajmer, that is Anna Sagar and Foy Sagar. However, the supply of water is made by retaining the rainwater which is available for a very short period of time during the monsoon months. For about 90 days, the rainfall may occur intermittently, and depending upon the runoff characteristics in the area, the water is impounded in these two lakes. So, keeping the characteristics and the requirement in our minds, now let us look at the watershed characteristics of the two. Rainfall analysis is to be carried out for the sub watershed of Anna Sagar, which is of the order of about 40.8 kilometers square. On the basis of the information available from topographical maps and satellite data, it has been found that the stream order is of the 5th order and the drainage pattern is dendritic, which means that the soil is quite fissured and fractured and has the potential for the infiltration capacity. Similarly, analysis are to be carried out for recharge potential, and this is to be done for all the sub watersheds. It has been found that the stream order varies from 3 to 5, whereas the overall drainage pattern is dendritic in nature. Furthermore, we also find that through this area there are at least 4 faults which are passing through, of which 2 of them are big in size and cut across the whole watershed. In order to carry out the study, the following data were used for extraction of information. First of all, the Survey of India topographical sheets at 1:25,000 for 45 N, J, end and J 10, 1, 2, 3, 4, 5, 6 and 45 N, J 11, 2, 3, 4, 5 and 6 were taken, as these take into the whole area into consideration. Similarly, the satellite data for the area for the year 1977 Landsat MSS was available, and for the year 2002 IRS 1D list 3 data set was available. Fortunately, there was access to some aerial photographs, and thus the urban settlement map of that particular time could also be prepared. This information is the base information for the analysis. In such type of analysis, the role of human beings is very important, and thus demographic data was also taken into consideration. Data sets from the year 1981, 91 and 2001 census were taken to identify what is the growth pattern in this particular region and how the urbanization also increases with the increase in the population in that particular region. Various informations such as the total population, male, female, child population, the sex ratio, these were incorporated, extracted from the census data and were used in the analysis procedures so that a holistic solution could be arrived at. Furthermore, the master plan of the drainages were also available from the Ajmer Development Authority. The groundwater informations were obtained from Central Groundwater Board, and the meteorological data regarding the temperature, rainfall, wind speed and other informations were available from IMD, that is Indian Meteorological Department, New Delhi. and offices located within the state of Rajasthan, that is Jodhpur, Jaipur and Ajmer. Now let us look at the methodology which was adopted in order to undertake this study. We have already discussed the data collection procedure. The next task was to undertake image analysis, and in this case image rectification and classification of land use had been carried out. Image rectification was important because the area was falling over two satellite scenes. So, they had to be merged together to have the same sort of relationships, and then classification for the land use was performed. Having done this, the next step was the GIS database creation. In this particular database creation, informations were extracted from the drainage maps, the contour maps, the slope maps, the soil maps and other informations such as estimation of urban growth were incorporated. Having created the GIS database, the runoff analysis using a hydrological model was carried out. The model so selected had one basic requirement to be met, that it should be able to perform both the runoff and the groundwater recharge computations. On the basis of the results which are to be made available from the hydrological modeling, the next step was to undertake the impact of urbanization on surface runoff and groundwater recharge. This slide gives us a view of the two satellite images which were taken for the studies for the year 1977 and 2005. And here in this particular image, one can see both Phoi-Sagar and Anna Sagar in the central portion as two black patches, but on the right hand side of the slide, on 2005 image, Phoi-Sagar has by and large vanished and Anna Sagar has reduced by a large extent. What we can see is that in the adjoining area there are large growth of urban activities which have taken place, that is, there has been encroachment into the lake area itself due to rise and pressure of urbanization. Based on the satellite data available, the land use maps for the year 1977 and 2005 were classified using maximum likelihood classification. Care was taken that the training data samples which were selected, they met a high order of separation amongst the information which was there. The classification was carried out to identify 9 different types of information which could be of importance for hydrological modeling. The land use classes which were identified are barren land shown in light pink color, rocky terrain in light orange, exposed rocks as white, mixed vegetation as green, sandy soil as light blue, settlements in magenta color, shrublands in light green color, water body areas in dark blue color and wet alluvium lands in grey color. When we compare the two images of the year 1977 and 75, one can see the rate, the impact of the urbanization which is there. Foy Sagar, which is at the left hand edge on the left hand image as a linear body, is no more visible in our year 2000 map. That has been totally engulfed and has been classified as barren land. That means one water body has now disappeared. Similarly, when we look at the Anna Sagar, which is lying at the central portion and is a big blue patch on the right hand side, it has reduced to a very small area, and surrounding it lot of urbanization has taken place, which means that now the hydrological characteristics in and around the Anna Sagar sub-watershed has undergone a major change in these 29 years, and thus the water spread of Anna Sagar has reduced significantly. This particular slide, the results of the image classifications are shown for different data sets which were available to us, and it is observed that the information that has been extracted through the classification procedure for all the cases is more than 90%, which meets the minimum criterion for accuracy classification to be accepted, which is universally at a standard of 85%. Based on the classification of the satellite data, one can now make an assessment as to how the built up area over a period of 29 years from 1977 to 2005 has increased. In the year 1977, the built up area in terms of hectares was only 488.03. In 1989, this got enhanced to 838.41. In 1991, it became 909. In 1994, it became 979, and it kept on increasing, and in the year 2005, this is of the order of 1463, which means that there is a substantial increase in the built up area, and it is approximately 300 times. This is a very alarming rate of growth in 29 years any region can have. Along with this, let us look at the population which was there. In the year 1977, about 3,31,000 people were there, and this population rose continuously at a very steady rate, and ultimately in the year 2005, the population is of the order of about 5,25,000 approximately. If we look at the increase in the population, the rise in the population is about 160%. So, it means that in order to accommodate the increase in the population, the conversion of pervious land to built up area is more than the rate of population, and it is nearly twice as per the rate of population growth, which means apart from providing residential areas, there are other activities which have also been catered to in order to meet the demands of the population in that particular region. Some of the major demands could have been provision of employment. That is, there should be opportunities for employment then only the population will migrate to that region. It is found that there is substantial industrial growth in this particular region, and this has encouraged the migration rate. Now, let us look at the runoff analysis that has been carried out. In order to carry out the runoff analysis, we have three sources of information from which the data has been generated. First is the thematic data. This includes meteorological data, soil type data, soil texture data, infiltration informations or parameters, population data sets ranging from the year 1951 to 2001, and drainage parameters in that particular watershed. For land use, as we have already discussed, remote sensing data sets have been used for 8 years starting from the year 1975 to 2005, and using digital image processing, the land use land cover maps have been generated. This has been also supplemented with Survey of India topographical maps at 1:25,000. All these inputs have been sent into a GIS environment wherein various thematic layers and model parameterization have been identified. The hydrological model which has been used takes into consideration the soil texture map, the soil type map, precipitation map, infiltration parameter map, population density map, land use map on a yearly basis, impervious and pervious area map, drainage maps, contour maps, spot height maps, digital elevation, slope map, aspect map. These all are inputs into the SWMM hydrological model which has been used for this study. In order to carry out the runoff analysis, the model has to be first of all calibrated. So, some year of data have been used to calibrate the model parameters which are there in order to generate the surface runoff, and this has been compared to the observed surface runoff which has been recorded at the Anna Sagar Lake. For runoff analysis, EPA Storm Water Management Model or SWMM has been used. Well, this is a watershed model and it is an event, it can be operated as an event based or as a continuous simulation model, wherein various hydrological informations can be incorporated into the analysis procedure. The uniqueness of the stormwater management model is that it has various modules for modeling purposes. These are rainfall runoff, rainfall model, runoff model, transport model and statistics model. The rainfall module takes long time series of precipitation records and generates interface files which is input to the runoff block of SWMM. The runoff module, it takes the rainfall data available from the runoff module and simulates the quality and the quantity of runoff which would be generated by various rainfall events which may be occurring. In order to simulate the ground, the runoff model can incorporate the following basic characteristics, which include land use, the topography of the area, the soil type. The model can take into considerations various processes in the watershed, which include evaporation, infiltration and surface storage. After the runoff has been generated, then this runoff is to be now routed through the streams and the river. So, it takes the runoff generated from the runoff model and routes the storm water through the system. In order to undertake the process of routing, it incorporates the stream channels and its various characteristics such as the slope, the length and the cross sectional areas. In order to carry out the runoff analysis of the storm water management model, the model requires a certain amount of setup, which include watershed delineation, the physical characteristics, the stream's physical characteristic, stream flow generation for calibration and continuous simulation for the monsoon period. This particular slide shows the layout of the Anna Sagar sub-watershed, and at the center we can see the lake region, and into this particular lake region there are three major streams which flow into it, and onto these major streams there are many other substreams which join into it. By and large, we can see that there is a mesh of streams which are contributing. Thereby, it suggests that the watershed is having a dendritic type of characteristic in terms of the drainage nature. So, what were the typical characteristics, physical characteristics which were extracted for each of the sub watersheds? These characteristics were determined or extracted from the digital elevation model which was there, and the parameters are area of the subcatchment, the general slope of the subcatchment, the length of the subcatchment, the width of the subcatchment, soil hydrological group distribution, infiltration capacity and percentage imperviousness in each of the subwatersheds. For model parameters and simulation, 3-hour rainfall for Ajmer rain gauge station was taken into consideration, along with daily minimum and maximum temperature, daily evapotranspiration which was available from the public health department, evapotranspiration which was computed from the evaporation, lake seepage which was again available from the public health and environmental department of Ajmer, infiltration characteristics, these are soil texture based, percentage impervious was extracted from satellite data, and various topographical parameters were extracted through GIS analysis. The simulation was in continuous mode for the monsoon period with 15 minutes time step. Based on this, the calibration was performed, and it shows that the runoff simulation for the year 2000 for Anna Sagar shows a very close match between the observed and the estimated runoff. During the dry period, the model tends to under simulate, but once a rainfall event has occurred, then the nature of simulation is very much in line with the observed information. Using this, one can now find out what is the relationship between the observed and the simulated discharge, and using regression analysis, this can be expressed as y is equal to 1.0681x minus 150809, where x is the observed runoff value and y is the estimated runoff value. Well, this relationship has a regression coefficient which is close to 0.99, which is a very good coefficient representation. Based on the calibration that was performed earlier, now the runoff generation for the 29 years under consideration was carried out starting from 1997, 1989, 1991, 1994, 1997, 2000, 2002 and 2005. These years have been selected because for these years the remote sensing data was available to us. And what we can see is that as the urbanization has increased, there is a stepped rise in the estimated runoff. In the early days of the monsoon, the percentage increase is not very high, but at the lower, that is at the end of the monsoon season, the surface runoff is enhanced by more than 60% or so. So, on the basis of this results, we can now make an assessment of the impact of runoff in terms of the peak runoff which is there. In the year 1977, the peak runoff in cubic meters was nearly 2 million cubic meter, and the impervious area was 41.58 hectares. When this value steadily increased in the 1989 to 2.23 million, and the impervious area became 167 million hectares. In 1991, this became 2.26 million cubic meter. The impervious area increased to 205 hectares, and by the year 2005, the peak runoff got enhanced to nearly to 2.85 million cubic meter, while the impervious area in terms of area got enhanced to 464 hectares. If we look at the percentage increase in the peak runoff, this is of the order of about 42%, while the increase in the impervious area is 1137%, which is a very large figure. And corresponding to that, we have an enhancement in the peak runoff. That is, this is the flood runoff which is coming. That means that when the floods are going to be there, the magnitude is going to be is already enhanced by 42%. Having looked at the runoff, now let us look at the groundwater recharge estimation. So, from the GIS database, one can now extract information regarding the groundwater observation wells, hydrogeological formation layers, watershed boundary layers, drainage contours and lineament layers. This is also supplemented by other ancillary data, that is, what is the groundwater levels, specific yield and pumping rate, and from the satellite data the land use, land cover there is generated, and using this information one can generate the slope map, the specific yield map, the water fluctuation map, and from the built up areas one can now take into consideration certain specific domains through which one would like to undertake the fluctuation of groundwater. Here, all those areas which are less than 20% in terms of slope have been considered, and using this criteria, the change in groundwater volume has been simulated and compared with the groundwater withdrawal and the seepage from the pond lakes, the recharge from rainfall has been computed. This slide, it shows the post and pre-monsoon groundwater levels for the year 2005, and what we can see is that the groundwater level in the pre-monsoon duration is very low, while as the rainfall has occurred and after the post monsoon, the substantial portion of the groundwater has fallen, and it is being depicted by the light blue color. The figure below shows the contour representations of the groundwater positions at the two time frames, that is pre and post monsoon period. The next slide shows the groundwater recharge areas, and what we can see is that how the recharge in these areas have taken place. Virtually in the Anna Sagar water catchment area, there has been very little recharge. You can see a large portion of the Anna Sagar is shown in magenta color, which is representing low recharge in the region in terms of the fluctuation which has come into the water level. So, based on this, we now look at the impact of urbanization on groundwater recharge from rainfall, and what we find is that this particular information shows that in the year 1977, the amount of recharge during monsoon period for the year 1977 was approximately 5.6 million cubic meter, which at present has got reduced in the year 2005 to nearly 3.9 million cubic meters, which means a fall of nearly 1.7 million cubic meters of groundwater recharge. This groundwater recharge shortfall is now going to create an imbalance in the hydrological cycle. So, now we can have a look in terms of the reduction in recharge with the increase in built up area, and what we find is that as the built up area is increasing, the recharge has decreased significantly. So, from this particular study, we can say that remote sensing coupled with GIS technique have proved to be an efficient tool for urban change detection and impact assessment studies. The rate of land development in Ajmer is outstripping the rate of population growth. Sub-watersheds have dendritic to subdendritic drainage pattern with very fine texture. Impervious surfaces have a significant effect on surface runoff and groundwater recharge. Surface runoff is found to be proportional to the impervious surfaces, whereas groundwater recharge decreases exponentially with an increase in the impervious surfaces. Dear viewers, with this lecture, I end this series of lectures related to modern surveying techniques. Here, the techniques that have been discussed are GPS, remote sensing, photogrammetry, digital elevation model, and GIS. Apart from this, some of the applications using remote sensing and GIS have been discussed, and these are education infrastructure development, building attribute and mapping, drought management, tourism planning, urban zonation planning, municipal GIS, reservoir sedimentation, impacts on urbanization. However, there are many applications using remote sensing and GIS which may not have been covered or discussed. The basic idea was to introduce the concepts and how these can be integrated together for various types of mapping and planning. At the end, I would like to express my sincere thanks to NPTEL for providing this opportunity to me to prepare video lectures on this important topic. I would also like to thank my colleagues Professor P.K. Garg and Professor Deepak Khare, who allowed me to refer to some of the application case studies carried out by them. I would also like to express my gratitude to my family for the extreme patience and support extended to me during the preparation of video material. Last but not the least, I would like to express my sincere thanks and gratitude to the video recording team at IIT Roorkee and the coordinator Educational Technology Cell for their unsolicited support and patience. Thanks for watching.